Hello everyone and welcome once again to our channel where we discuss various topics from your math, physics and other subjects like that. So if you're new to the channel, here we give you educational content that help you get better in class and outside of classroom. So this is our physics lesson for the SS1 students, and this is the sixth topic of the SS1 first term curriculum. And what we're looking at here is rectilinear motion. Now, to those that have been part of the video so far, we've been able to look at motion in detail. We've been able to tell the meaning of motion, the type of motion, and so on like that. We even looked at the causes of motion. And you recall that as one of the type of motion, we discussed translational motion, also known as linear motion. And I say that is the type of motion where all points on the body performing the motion go along the same path. That is, every point on the body are on the same path. So it's not necessarily a straight line motion. I could go in a curve also, as long as everything is going in a straight line. Like in the case of a projectile, when you throw something up at an angle, it also goes through that curve and end at a point, and it can be represented with linear motion as well. But today what we'll be looking at is the ones that are in a straight line. How can you define them? What are the terms you should look out for when studying motion in a straight line, hence rectilinear motion? Now, in this topic, what we're going to be looking at will be understanding the concept of speed. We'll also go into details with the concept of velocity, and then we'll learn acceleration as well. Now, you see, these three things are going to help us solve a lot of problems when it comes to rectilinear motion. So it's important that we get the details first, then we solve problems on them. Then after that, we then go to representing motion in a graph. Now, there are three graphs we're going to talk about. I'll be looking at the distance time graph, the displacement time graph, and velocity time graph. Now, note, I do know that velocity time graph is often the one that is taught in classrooms because it has a lot of importance to rectilinear motion, but it does not mean that distance time graph and displacement time graph are irrelevant. They are also relevant. So we look at how you can represent motion using these three graphs, and we look at how are they important to your study of physics, because that's what we want to achieve, to get meaning from what we are doing right here. And then to end it, we then solve many more problems on rectilinear motion. Now, if you're ready, we can go into this in detail, but I want to speak with you that you do ensure that you are subscribed to the channel. This is how we grow. We want you to click the subscribe button. It's only going to take a moment of your time. Kindly do so, and also hit the notification bell icon. So that way, every time we put out a new content on this channel, you will be notified. And please ensure that you like the video and share them so that we can reach a host of other students like you who need content like this. So if you're ready now, let's go into the breakdown of this topic, rectilinear motion. Hello everyone, and welcome to the sixth topic in the SS1 physics curriculum. Now, you know, as we do on this channel, that we give you educational content that make you better than the others. So this is the sixth topic in the SS1 physics curriculum, and the topic is rectilinear motion. Now, if you have been following the channel, you'll see that we've talked about motion in detail. We defined motion. We looked at the different types of motion. Now, most importantly, the translational motion. Now, if you recall from that video, I did mention that when we talk about translational motion, we often just say it is motion in a straight line, right? But it is not necessarily along a straight path. I did mention that you could also have the curvilinear type, that is like in the case of a projectile, when you throw a stone or when something is shot at an angle. Now, you see that it goes along a parabola path, right? But you can also solve problems like that using linear motion, because all of them still fall under the rectilinear motion or translational motion as we discussed. So what we are looking at in this case is how you can solve problems or how you can use them to define things around you when it comes to motion in a straight line. Okay, and in this topic, these are what we're going to be looking at. I will look at the concept of speed. We'll define what speed is, and then we apply it to solve problems. We'll also define what velocity is and the concept of velocity, and then we apply it to solve problems as well. You know that there are different types of speed as well. We have uniform speed, constant speed, the same thing with velocity, uniform or constant velocity. We also have the non-uniform velocity as well, just as we have non-uniform speed as well. We also look at acceleration. We define it. We look at the types of acceleration we have, and then we apply the knowledge there to also solve multiple problems on rectilinear motion. Now, when we are done with that, we then go into representations of motion with graph. Now, you see, linear motion can also be represented in a graph, and there are three major graphs we're going to look at this point. We're going to look at distance time graph, displacement time graph, and velocity time graph. Now, many of you may have heard of velocity time graph before now. Now, this is because it's one of the graphs that is used mostly to describe the motion of an object. However, we still have what is distance time graph and displacement time graph that are equally relevant. So we look at what do they look like and what do they tell us. What can we deduce from these three graphs? And then we use them to solve problems. We apply the knowledge to solve multiple problems in physics as well. Then we close by solving different problems from your WASE curriculum, from your JAM curriculum, and other things like that. We combine them to solve multiple type of problems that you will most likely face in the course of your study. So that's what we are trying to do in this video. Now, if you're seeing this video for the first time, let me say welcome to our channel where we give you educational content that help you grow. So please ensure that you are subscribed to the channel, and we also plead that you click the notification bell icon. This way, every time we put out a new content, you will always be notified. We urge you to join us and grow with us, and please ensure that you like the videos and also share them. So this way we can reach many other students like you who need content like this. So please like, share, and subscribe. So now we'll be going into details of rectilinear motion. I hope you're ready. Get your writing materials and let's learn. Let us now look at the concept of speed. Now, first thing we have to establish is that when we define motion, we said it involves an object changing position with respect to time. That is, the object was at a set location, and then over time, it is now in a new location. And then we look at how it moves from that point to where it is and the time it takes for that to occur. And that's how we describe motion. That's why we describe motion by either how the object moves or the time it takes to make those movements. So you see, when we talked about type of motion, we talked about types based on how they move, such as linear motion, rotational motion, random motion, oscillatory. And then we say in terms of time, where we talked about uniform motion and non-uniform motion. Right? So we see here that time is a factor. The distance can also be a factor when you are discussing motion. Now, and since we are looking at rectilinear motion, it's important that we understand the concept of speed. Now, we use speed a lot in our vocabulary as how fast or how slow an object is. But let's look at it from how physics sees it. Now, for example, when we talk about speed, we often recall the fastest man alive, Usain Bolt, to be able to cover 100 meters in 9.58 seconds. Record time, okay? That is, we looked at the distance he covered there and the time it took for him to cover it. And that is how we got the speed, the fastest speed a man can run, okay? So this is how we also define speed in physics. We look at the distance covered and we ratio it with the time taken. So basically, speed is distance covered over time taken. So if we're going to define it, we'll say speed is defined as the rate of distance covered. Okay, you can also say the time rate of distance covered if you like. So basically, speed is distance covered over time taken. Now, you also recall that in our earlier classes in physics, I did mention that in physics, any measurement you take without unit is obsolete. It is not counted as anything that has meaning. So in physics, not just numbers, we also look at the units of things. So the unit of speed is important to us. Many of you already know this because we talked about speed also during that class when we talked about dimensions and units. So the unit for distance is meters, and that for time is seconds. So speed is measured, it is measured in meter per second. Okay, so this is how we define speed. This is how we calculate speed. So we look at the distance the object covers and the time it takes it to cover that distance. And just like that, you've gotten the speed of that object. Now, it's important to note that we just look at the distance to cover. We do not care the direction in which it takes. Okay, that is all we measure there is the total length of the path the objects go through. Okay, and then the time taken to do this. So it is a scalar quantity. It does not involve direction, so it is not a vector. It is scalar. Okay, and when we are trying to measure speed, you agree with me that we do not cover the same equal distance in equal time. It's very difficult for people to do this. Doesn't mean it's not possible, but it's difficult. So this means we have different type of speed. This gives rise to the different type of speed that we have. So let's cover them all. Type of speeds. Type of speed. We have what is known as uniform speed. Now, what does uniform speed means? Now, we say an object has a uniform speed if it's able to cover equal time, a distance in equal time interval. Like for example, if an object is going through 100 meters and during the first 10 meters, it does that in 1 second. And then the next 10 meters in also 1 second. The next one in also 1 second, and it covers that, completing the 100 meters in 10 seconds. Okay, that kind of object is going through what we know as uniform speed because it covers equal distance in equal time interval. So when object covers equal distance in equal time interval, okay, that is uniform speed. Once again, if the object is covering 100 meters and each 10 meters is covered in 1 second each, completing it in 10 seconds for the 100 meters, then that is what? Uniform speed. Now, there's another one known as non-uniform speed. Non-uniform speed. Of course, it is the inverse of this. When you do not cover equal distance in equal time interval. Now you are going through 100 meters. Now the first 10 meters may be covered in 1.5 seconds. And then it gains more speed and covers the next one in say 1 second. The next one in maybe 0.9 seconds. And it continues like that. And then at some point, it's getting tired, then covers the same 10 meters now in about 1.9 seconds. You see that the time interval is not the same, right? In that case, what we have is non-uniform speed. So, when object covers equal distances in different time, interval, this is non-uniform speed. Okay, we have another one that is known as instantaneous speed. Okay, now this one is often used when object is traveling from point to point and then we want to see the speed at a particular instant. Take for example when you see the traffic police on the road and then there is a speed limit at that particular road. they often use a device to measure the speed that those vehicles pass at that point, and then they use that to catch the violators of the speed limit at that location. Now, what they do is they use that device to measure the instantaneous speed. That is the speed of that object at that particular instant. Okay, so that is what we mean by instantaneous speed. So you could have been going slow before then, but at that point, what is the speed you are going at is what that instrument that they use measures. Okay, the same car could have gone slow at some point and could have gone fast at some point, but at that point they measure it to see if it is over or under the speed limit. So like I said, instantaneous speed, the speed at that particular instant. Okay, so this is the speed of an object at a particular instance. Okay, and then there's another one known as average speed. Average speed. Now, to explain this, if you were going on a road trip, right, you agree with me that there will be some time where you'll be moving very fast, especially where you are on the express and there isn't any traffic at all. And then there will be time when you have to slow down. Perhaps you are in a school region where people will be crossing the road and you don't want to meet with an accident or you don't want to hit anyone. So you have to go slow at that point. You pass through some places where there is speed limit and you can't go over that speed limit. Even if you are driving the fastest car, you have to go under the speed limit at that particular region. So you see that you go at different speed at different instances while on that same road trip. But yet it is possible for you to calculate your ETA, that is your estimated time of arrival. Now this is because over that distance, there is an average speed you can get. That is the total speed divided by the number of speed you have. So if you have like 10 speed recorded, right, and then you add them together, divide by the number of speeds, you can get your average speed. Okay, that's the case of average speed. So these are the 4 types of speed: uniform speed, non-uniform speed, instantaneous speed, and average speed. This average speed is often given as when you have V1 plus V2 plus V3 plus ... plus Vn, all divided by n. This is how you get the average speed of an object. Now, all of these are relevant to calculation. So what we're going to do next is we look at some questions that has to do with speed, and then I show you how we can solve those kind of problems. Now, let's take a look at this question. The question says, find the average speed of a boy who runs 200 kilometers in 30 seconds. Now, I did mention that of the type of speed we have, one of them is average speed. Now, when you have different speed and then you add them up and divide by the number of speed given, you get average speed. But in absence of that, you can also get the average speed of an object by looking at the total distance covered over the total time taken. That is, just like we said, all the distances over all the time. Okay, so since all the distance here is 200 meters and the total time is 30 seconds, we can get the average speed of the boy. But before we go on to solve this, please, if you're yet to be subscribed to the channel, kindly take a moment of your time to hit the subscribe button, and don't forget to also click the notification bell icon so that you get alerted every time we put out a new video. And please ensure that you like, share, and share the video as well so that we can reach many more students who need content like this. Now let's solve. Solution. We want to find the average speed. So the average speed is total distance covered over total time taken. Okay, now if we apply this, the average speed would then be, the total distance is 200 meters, the total time taken is 30 seconds. Now, when we divide this, 30 goes in 200, we can easily say 0 here, cancel out the 0. Now, 3 in 20, that is 6, remember 2, so 2 over 3, and that will give you 0.667 meter per second. So the average speed of the ball is 6.667 meter per second. Now, please take note. Some questions will ask you to leave your answer in said number of decimal places or to the closest whole number, amongst other kinds of ways you can approximate a value. So you always have to solve it based on that. But whenever the question does not give you such kind of instruction, at best ensure that you have 2 decimal places if there are decimals involved. But in this case, I have chosen to leave it in 3 decimal places, 6.667 meter per second. This question says a bus travels with an average speed of 60 kilometers per hour. How long does it take to cover a distance of 500 kilometers? Now, when students are faced with this kind of question, what they often ask is, are they to solve this in the SI unit? You know that we are asked to find the time here, and time is measured in seconds, right? But when you see questions like this, here are some things you should look out for. Now, first off, you see the speed given here is in kilometer per hour, right? And then the distance given is in kilometers. Easily, you see that both have kilometers in their unit. Okay, so you can work with this directly and get your answer in hour. Now, if the question then tells you to leave your answer in seconds, go ahead. If the question doesn't tell you and you leave it in hours, you are still fine. Okay, except if it is stated that leave your answer in the correct SI unit, or in a case where both of them are in different type of units, then you have to bring them to a uniform unit and make it work. So since both have kilometers there, I can just work and get my time in hours. So let's solve. Solution. We know that speed is distance over time, right? And we are asked to find time. So that means the time taken will then be distance over average speed. So let's apply this. So the distance is given as 500 kilometers and the speed is 60 kilometers per hour. Okay, so kilometer cancel kilometer, so our answer will be in hour because this can be taken to the numerator now. Now we have 500 divided by 60. So time taken would then be 8.33 repeated in hours. So 8.33 hours will be the time taken for this bus to cover 500 kilometers. In this question, we're asked that how much longer would it take to travel a distance of 600 kilometers at a speed of 50 kilometers per hour than it would at a speed of 60 kilometers per hour. Okay, so we are comparing these two speeds together. Right? Now, I need you to take a moment. You can pause the video if you like, and then try to solve this question yourself first. Now, you then compare what you have gotten to what we get at the end of this video to just see how well you have improved. Okay? So, now let's solve. Now, one thing you can do here is to either find the time taken for each of the speeds. First, you can first do the case when you have 60 kilometers and the case when you have 50 kilometers and then find the difference. Or you can put both of them in the same equation. Okay, so for the purpose of better learning, I will do them separately so that you understand the concept. Okay, and then we go on to find our final answer. So first, time taken. So when speed equals 50 kilometers per hour, the time taken would be the distance 600 kilometers divided by speed 50 kilometers per hour, and this would give us 12 hours. And then when speed equals 60 kilometers per hour, the time would be 600 kilometers divided by 60 kilometers per hour, and this will give us 10 hours. Now, time difference. Time difference will then be 12 hours minus 10 hours, and that will give us 2 hours. So meaning that if a particular vehicle is going at 50 kilometers per hour, it will take it 2 hours more to complete 600 kilometers as compared to another vehicle going at 60 kilometers per hour. And this is the solution to the problem. In our everyday life, our students and almost everyone use velocity and speed interchangeably. We often think that they mean the same thing, but there is a clear distinction between the concept of speed and the concept of velocity. So let us look at what velocity is and the types of velocity. We define all of this as well. Now, when we talk about speed, we see that the time taken to cover a distance is the speed. But in the case of velocity, the direction is very important. So in what direction is the object traveling can affect the velocity of said object. So this is why we call velocity a vector quantity, while speed is a scalar quantity. But what is the definition of velocity? So in the case of speed, speed relates with distance, but velocity relates with displacement. Now, when we talked about distance and displacement, we said distance is the total length of path that an object travels, while displacement, right, is the distance traveled in a specific direction. So that is the case when we are talking about velocity as well. So let's define it. We say velocity is defined as the rate of change of displacement. Okay, so basically what we are saying here is that velocity equals displacement over time. So you see, what changes here is displacement. For speed, you have distance occupying the space here where displacement is. And speed and velocity are different in terms of distance and displacement, where displacement is the distance traveled in a specific direction. Now, when it comes to types of velocity, in this case also, we have uniform velocity, we have non-uniform velocity, okay, we have instantaneous velocity, and then we have average velocity. And the definition of this is also similar with the definition of the types of speed that we have. The only thing we have to do is replace distance with displacement. So uniform displacement will be when an object covers equal amount of displacement in equal time interval. No matter how small the time interval may be, that will be uniform velocity. And then non-uniform velocity means that it does not cover the same displacement in equal time interval. And then instantaneous velocity will be the velocity of an object at a particular instant in time. And then the average velocity will be the total displacement over total time taken, right? Or the addition of all the velocities given over the addition of all the numbers of velocities that we have. That is an average value of the velocities given. So this is what we know as velocity and the different types of velocity. Now, don't forget, that if you have any question at all, you can drop them in the comment section. We expect your questions and your contributions to the topic. Please drop them in the comment section, and we promise to attend to every one of your comments. So now let's look at how we can solve questions involving velocity. Let us solve this question involving velocity. Now the question says a train heads south covering a distance of 2,400 meters in 1 minute. Find the velocity. So we see here that it's going in a specific direction. So when you solve, you be sure to end your answer in meter per second and then the direction, which is south. So here's how we do that. Solution. Now before I go on, there's something you would see here, that the distance here is given in meters, which is the SI unit for distance, but the time is given in minutes. So what you have to do here is to convert this into seconds. Okay, so we have distance covered is 2,400 meters. Okay, so since it's heading south, we know that it's a displacement in this case. And then time taken equals 1 minute. Okay, which is actually 60 seconds. So velocity should be displacement over time. And this would give you, now the displacement is 2,400 meters south. The time, 60 seconds. Now from here we can see that velocity is going to be 2,400 divided by 60 would give us 40. So that's 40 meters per second south. And this is how we solve a question like this on velocity. This question says a student walks 60 meters east in 30 seconds, then turns around and walks 40 meters west in 20 seconds. Now we have to calculate the total distance covered, the displacement, the average speed, and average velocity. Now here's how we solve this. So for the A part, where we have to find the total distance would be the sum of all the length of the path the boy has walked, the student has walked rather. So since this is 60 meters and then later 40 meters, would have 60 meters plus 40 meters to give us 100 meters. So the total distance walked by the student is 100 meters. Now, the B part. The B part says we should calculate the displacement of the student. Now, the student has walked 60 meters east, then turned back and walked 40 meters west. Now, let's take this to be the start point. And then the boy walks this distance all the way to this point. So if this is point A and then point B. Now the boy walked 60 meters to get to point B and then walked back to point C here. Now this here is 60 meters, this here is 40 meters. Now the displacement is going to measure just from here to here. So that means displacement, remember, in a specific direction to this point C, would be 60 meters minus 40 meters. And this would give us 20 meters. In what direction? So since this is the start point, it's still heading east. So 20 meters east. That's the displacement of this student. Now, let's get to C. C says we should calculate the average speed. Now, average speed is total distance over time taken. Okay, and this would give us the total distance. We have already solved that to be 100 meters. Now the total time, we have 30 seconds here and 20 seconds. That's 30 seconds plus 20 seconds. Now this would give us 100 meters divided by 50 seconds. That means we have 2 meters per second as the average speed of the student. Now finally, D says calculate the average velocity. Now velocity, average velocity is displacement over time taken. Now the displacement we've also solved, that will be 20 meters east. Now we divide that by the time taken. Now the time it took the same student to get to this point is the time it took the same student to go all this way and back here. So it's still 50 seconds. Now making the velocity to be 0.4 meter per second heading east. So here you see that speed and velocity are not the same thing. You see here we have to consider the direction in which the student has walked as compared to this where we just looked at the path length alone. So this is how you solve questions like this. You recall that when we were talking about velocity, I mentioned that velocity could be uniform or non-uniform. Now the non-uniform means that velocity is changing periodically, that is with time, it's changing with time. There was an initial velocity and then it changed to a new velocity and then could change to another one and so on like that. Okay, now that gives rise to what we know as acceleration. So which is why we want to look at what is the meaning of acceleration and then how can we solve problems involving acceleration. So first, let's define acceleration. We say acceleration is defined as the rate of change of velocity of an object. Okay, that is, we're looking at the rate at which the object changes velocity. Now oftentimes we say acceleration equals final velocity minus initial velocity over time. Okay, and from what we have here, we often denote final velocity as v and initial velocity as u. So we say final velocity is v, initial velocity is u, and then time is t, and acceleration is a. Now when we put all of this together, it means a equals v minus u over t. Now this itself is very important because it gives rise to what we know as the first equation of motion. Now because when we work with this, we can cross multiply and then say at equals v minus u, or basically we say v equals u plus at. Now you see this here is the first equation of motion. We use it a lot. There are other two equations. I will show you how we can derive them from this. But for now, note this, that acceleration is what? The rate of change of velocity, which when we write it mathematically, we'll say a equals v minus u over t, and it gives rise to the equation known as v equals u plus at. So this is how we define acceleration, and this is the equation we use to work with it. But please take note, there are other two equations which I'll show you in the next video. When we are solving questions involving rectilinear motion, especially with objects that accelerate at a certain rate, there are some equations we use. Now those equations are called the equations of motion, and there are about 3 of them. Now you might be familiar with them, where we have v equals to u plus at, and then we have another one that says s equals ut plus half at squared, and then we have another one that says v squared equals u squared plus 2as. where v is final velocity, u is initial velocity, a is acceleration, t is time, and s is displacement. All of these carry their natural definition. However, how did we come about these equations? Now, I had shown you when we were talking about acceleration how we got the first one, but I'll go over that again and then show you how we got the second equation and then the third equation of motion. So let me break this like so. Now observe. Now for this first equation, how we arrived here is from the definition of acceleration. We said acceleration itself is change in velocity, that is v minus u over time. And then from here we say at equals v minus u. And of course, when you make v the subject, v therefore becomes, now minus u comes here and becomes positive, okay, then plus at. And this is the first equation of motion, v equals u plus at. Now you can use this to solve several questions on rectilinear motion, but it's not limited to this. Now to get the second one, we use a concept known as average velocity. Now we know that distance is supposed to be average velocity multiplied by time. Okay, so using this concept, let's see what we get. To get average velocity would be the sum of velocity, so final velocity plus initial velocity divided by 2. Okay, now but we already know that v equals to u plus at, isn't it? So we can now say average velocity equals, in place of v, we have u plus at, then plus u over 2. So average velocity therefore becomes 2u plus at over 2, which basically is 2u over 2 plus at over 2. Now from here we can say average velocity is u plus half at. Okay, now all we need to do is put this into this equation now, and then distance or displacement s will now be average velocity times time. So what's average velocity? U plus half at multiplied by time t. So s therefore becomes, now u multiplied by t, that will give you ut plus half at times t, that will give you half at squared. So you see how we arrived at this equation now, right? So that's the case here. Now let's derive the third one. To derive the third equation of motion, we started at v equals u plus at. Now what we did is we square both sides. So that is v squared. Let me write that first. Square both sides. Square both sides. Okay? Now that will give rise to v squared equals u plus at multiplied by u plus at. Okay? And this would give you v squared equals, now take your time to expand this. You should arrive at u squared plus 2u at plus a squared t squared. Now, I want to do something here. Now, observe this. V squared equals u squared plus 2u at. Now, this, I want to make sure it has what we know as the coefficient 2. So, to put the coefficient 2 here, I will write it as 2a squared t squared divided by 2. So that there's a 2 here. But no, 2 divided by 2 is still 1, which is the coefficient we have originally here. Now, these two now, we can say that they have 2 in common. But I'm only going to call one of the a's also. So what we'll have here is v squared equals u squared plus, now these two, they have 2 in common, they have a in common. Now even though they have t, I'm not going to call that out. Now observe what we're going to have left. Now if you take 2 and a out of this, you are left with ut, right? Now plus, you've taken 2 here, we are left with 1 over 2. Then we've taken one of the a, so we have a, and then t squared remain. Now you see why I did not take out the t is because what we will have left here will look like what we have already derived at this point. Okay? So, but ut plus half at squared equals displacement s. So we can now say v squared equals u squared plus 2a, then all of this is s. V squared equals u squared plus 2as. So these three equations are going to come in handy as we solve problems on rectilinear motion. So you can start by knowing the three of them if you like, or you just go through this process so that you can derive it every time you need it. But it's easier to just memorize as we go on. But these are the three equations of motion used to solve problems on rectilinear motion. Now that we know the various equations that can be used to solve rectilinear motion, especially with accelerated objects, let's try to solve this one. Now this one says a motorcycle accelerates from 5 meters per second to 25 meters per second in 4 seconds. What is the acceleration? What is its acceleration? Now to solve this, let's look at what we have. Now, one thing I tell students is, whenever you have question on rectilinear motion, do not forget the three equations of motion and try as much as possible to make sure that whatever you are solving does not have two unknown parameters. Now, the three equations, as mentioned before, is v equals u plus at as the first equation. Then we have s equals ut plus half at squared. And then we have v squared equals u squared plus 2as. Okay? Now, what do we have in this question? Now, we have initial velocity u. So given u is 5 meters per second, final velocity v is 25 meters per second, and time t is given as 4 seconds. And we are asked to find a, acceleration. So we have to look for the equation that has u, v, t, and a. Okay? So when we look at this, you see here there is no v here, so we can't even use this. We might be able to use it, but we don't have s. So since s is not given, that will be two unknown, s and a. Just like we have s and a here, two unknown. So the only equation that works here is v equals u plus at. And if we try to make a the subject of the formula there, we then say a equals v minus u over t. So v, 25 meters per second, minus u, 5 meters per second, all divided by 4 seconds. That gives us acceleration to be 20 meters per second divided by 4 seconds. And 4 in 20, that gives you 5. And what we'll have here as the unit is meter per second squared. So the acceleration of this motorcycle is 5 meters per second. In this question, we have that a car starts from rest and accelerates uniformly at 3 meters per second square for 5 seconds. And we have to find the final velocity. Now, you can pause the video at this point. Please note that I have put the three equations for motion up here for your use. Now, I want you to look at this question itself, write out the parameters we are given, and deduce the equation that will help us solve the final velocity. Now, have you come up with the equation that will work? Let's see what you have. So, to solve this, now we are given that the car starts from rest. So if it's starting from rest, that means it has no velocity at the beginning. So initial velocity u is 0 meters per second. Okay? And we don't have v, so v is unknown. That's what we are asked to find. And then we are given that the acceleration a is 3 meters per second squared. And then we are given that time t is 5 seconds. So to solve for v, the equation that works is v equals u plus at, because v is the only unknown and we have the other parameters in this question. So let's solve. Therefore, v equals from u plus at, we can then say v is 0 plus a, which is 3, multiplied by t, which is 5. And then v equals 15. Now, remember that this acceleration is in meter per second squared. So we're going to multiply that by seconds. Okay, so seconds cancel one of these, so leaving us with 15 meter per second. So you see that is the correct SI unit. So the answer to this question is 15 meters per second. This question says a bus moving with an initial velocity of 10 meters per second accelerates at 2 meters per second squared for 6 seconds. Find the distance covered. Now take a moment, write out the parameters given in the question, and then seek out which of these three equations written here would help you solve the question. So to solve this, you could go two routes. You could go the long way to first apply this equation here to find the velocity v. Then when you get it, you can then apply it into this one to now find the distance s. Or you could just do it straight away by applying this to find the distance. Since we have initial velocity, we have time, and we have acceleration. So we can just use this second equation to solve it all the way. So the solution would be, first, given that initial velocity u is 10 meters per second, and we're given that acceleration a is 2 meters per second squared, and the time t is 6 seconds. We can then find s. S equals ut plus half at squared. So s equals u, that's 10, and that is meters per second multiplied by t, which is 6 seconds, okay, plus 1 over 2 multiplied by acceleration, which is 2 meters per second squared, all multiplied by time t, which is 6 seconds. Then we square this. Now what does this give us? This would give you 60 meters plus, of course, 2 cancel 2 here, and this will give you 36. Okay, 36 seconds squared. So what we'll have here is, from here, we're going to be having 36 meter here. This second square will cancel this second squared, so we are left with just 36 meters. Now when we add all of this, we get 96 meters as the total distance traveled by this bus. So this is the solution to this question. Now if you have any question at all, whether it's from your study time, you came across a particular question on rectilinear motion or any other topic in physics, and you like help with it, please drop it in the comment section, and we promise to attend to all of your questions. Just keep them coming, and as always, don't forget to like, share, and subscribe to the channel. When you take study of the motion of an object, you can represent that motion in a pictorial form, or what we call graph. Okay, now this gives rise to what we know as the distance time graph, displacement time graph, and also velocity time graph. Now in this video, we'll be looking at distance time graph and displacement time graph. Now they're a bit similar with just a little bit of differences between them. So let's take a look at them one after the other, starting with the distance time graph. Now when you have distance time graph, that is, you're looking at the motion of an object. You have looked at the distance covered by that object and the time interval in which it covers these distances, and then you plot it in a graph. For example, if you have an object traveling a total of 200 meters, now and then you record the time it takes this object to cover some set distances within the 200, you can develop the distance time graph. So basically what you have is a graph like so, where you have your y-axis and then your x-axis. Now in the distance time graph, the distance is on the y-axis, so this represents distance. So let me just write this way so you can see clearly. And remember, distance is measured in meters. And then on the x-axis we have time, which is measured in seconds. Now compare this as well with the displacement time graph. Now, displacement time graph, we have displacement here. also in meters, and then time on the x-axis. Now, whenever you create this kind of graph and then you have different plotted points there, now mind you, while doing your distance time graph, you could end up with a straight line like this, or you end up with something like this. Now please note all axes remain the same. You could end up with something like this as well, and the same thing applies here, something straight or curved. Now there's a difference between them here. Now when you have a straight line for your distance time graph, it means that your speed, right, is you're covering equal distances in equal time intervals, so you have a uniform speed. Okay, a uniform speed. The speed remains the same as you go like that. Okay, and the same thing applies to the displacement time graph. Now here's the difference. Remember here, if you are to take the slope, let's say you are taking a slope of this line, what you are having here is change in distance, right, over change in time. And what does this represent? If you recall, speed is distance over time. So basically, the slope of this type of distance time graph would give you the speed. And in this case, if you take a slope here, what you have is change in displacement over change in time, which is basically velocity, which is displacement over time. So you see there, in this case where you have uniform speed, here you have uniform velocity. But when you have a curved line representing your distance time graph, what this means is that the velocity is changing. Okay, the speed rather in this case is changing, and here this means velocity is changing. You don't have constant or uniform speed as to velocity in these two cases here, right? So it means at this point the speed is at a different level. When it gets here, the speed changes again, leading to this curve, right? Remember, when you are plotting your graph, you look at the distance traveled and then you plot it against time, and then you represent this by drawing your plotted point, something like this. Okay, but in this case you now see it form a path that is curved, and in this case also a path that is curved. But in these two cases you have straight lines. So what it just means is that this one is uniform speed, this one is non-uniform speed. This is uniform velocity, this is non-uniform velocity. Now another thing that we can draw from this type of graph is that the steeper the line, you can also use it to tell how the speed is. When you have very steep lines like this, something like this now, shows that the speed is very high. Okay, and then when you have the type that bends down this way, it means that you have slow speed, right? Because it takes more time at this point to cover a short distance. So the speed here is slow. This means you have a slow. This means you have fast. Okay, so because here you see it covers more distance in a short time interval. So fast speed, slow speed. But remember, this is uniform speed and this is uniform velocity, while these ones are non-uniform. So with this, I hope you understand what we mean by representing the motion of an object in the distance time graph and the velocity time. In the study of the motion of an object, we can represent the motion of an object using the distance time graph or displacement time graph. Now, what each of them mean is as follows. Let's start with the distance time graph. In the case of a distance time graph, now this is a graphical representation of the motion of a body where we plot the distance traveled on the vertical axis and the time taken on the horizontal axis, or what we call the y and x axis. So meaning you have a graph like so, and then on this vertical axis, which you call the y-axis, you have distance. Now let me write it this way so you see clearly. Distance, okay, measured in meters. And then on the x-axis, horizontal axis, we have time. Okay. Now, whenever you represent the motion of a body in a graph form like this, you have what we call the distance time graph. Now, most times when you have uniform speed, for example, you usually have a straight line like this. Okay, let's say this being the path for the plotted points we have for a distance time graph of a particular object. Now, what this means is this. When you take the slope of this graph, you are having change in distance over change in time. Now, this is the slope m. Okay? Now, from this, what do we mean? Remember what we said, speed is what? Distance over time, isn't it? So, if speed is distance over time, so the slope of this graph, m, therefore becomes speed for that particular motion that you are studying. Now, another thing you can get from the distance time graph of a particular motion is this. Now, there are different types of distance time graphs you can get. If you have very steep line, like a steep slope like this, what this represents is fast speed. Okay? Then when you have a gentle slope, that is something that goes like this, it follows a path like this, straight line. Remember, all these three are straight lines. What you have here is a slow speed. Now, let me explain what this means. Now, if you look at this line, you see that the distance from start to finish of this motion is very small as compared to the time taken. So it covers a short distance in more time. That is why it is slow speed. But in this case that we have a steep slope, you see that the distance covered within a short time is very high. So that is why we have a fast speed in this case. So this is something you can learn from how the slope is. If it's a very steep slope, that is fast speed. If it's a gentle slope, then it is a slow speed. However, you can also have a distance time graph that looks like this. Distance time. That has a curve. Now, when your distance time graph is a curve like this represents changing speed. Okay? It means that the speed of the object is changing, is a non-uniform speed. That is why you see the path that this graph takes is a curved path. So when you have this type of graph in your distance time graph, these are the things you can get from it. First, you can tell if it is linear like this, you can tell whether it is fast or slow, right? And then you can also tell if the speed is changing when you have a curved line like this. Okay? Now, the same thing applies in the case of the displacement time graph with just a little variation. Now, in the displacement time graph, on the y-axis, what you have is displacement. Okay? Displacement, also in meters. And then here you have time in seconds. Okay? And you know that the difference here is that distance is scalar, displacement is a vector. So there is direction involved in this case. So, and the same way you could have this here, you can have your plotted point along a straight path like this. Okay? And the slope of this slope of a displacement time graph gives you your velocity. Okay? Because it is change in displacement over change in time. That is for this case. And as well, when you have a very steep slope like this, it means you have fast velocity. And then when you have a gentle slope like this, it is a slow velocity. And just like in the case here, you can also have a curved one, which means you have changing velocity. When this is displacement and this is time in seconds, this in meters. Okay, so this shows you that you have changing velocity, while this tells you that you have uniform velocity. So let us indicate them. This represents what? uniform speed, while this represents changing speed. Now this represents uniform velocity, while this is changing velocity. So this is what the graphs look like. So in case you find graph and you're asked to interpret, you can tell whether you have fast speed, slow speed, or whether you have changing speed. Fast velocity, slow velocity, or changing velocity using the distance time graph and the displacement time graph. If you do have any question, please ensure that you put it in the comment section and we'll definitely attend to all of your questions. When representing motion using pictorial form, the displacement time graph and distance time graph are not the only ways we can do that. We can also represent motion by using the velocity time graph. And just like in the case of the distance time graph and displacement time graph, the velocity time graph is a graphical representation of the motion of an object where the velocity is on the y-axis, that is vertical axis, and the time taken is on the horizontal or x-axis. Okay, it looks a bit like this. So you have a graph. Please pardon my freehand drawing. Here you have velocity, which is in meter per second, and then time in seconds. And then you begin to plot. At a set velocity A now, you take time x, you plot that part. At another velocity B, it takes time y. Yeah, so we plot that part also like this. And then you join it with a straight line. Now this is what the velocity time graph looks like. Now it is not limited to this particular outlook. It's all about how you plot the graph. So sometimes you can have something like this, sometimes you could have something that looks like this, or the other way around. Sometimes you could even have those that form a trapezium like this. But as you solve problem on it, you will see how all of these graphs come to form different shapes. Now, the things that we can learn from the velocity time graph are as follows. Now, when you have a velocity time graph, note that the slope of a velocity time graph is acceleration of motion. Now, to show this, let's take a particular velocity time graph that looks like this, that just has a straight line like this. Now, what this tells us is that if we have velocity here and this is time, okay, and then we take the slope here, the slope is going to be delta V over delta T. That is change in velocity over change in time. And you recall that acceleration is change in velocity over time. So you see why the slope of a velocity time graph gives you your acceleration. Now, another thing you should also learn from this is that the area under a velocity time graph, the area under a velocity time graph gives you displacement. Okay? If you're given any velocity time graph and you are asked to use the graph to find the displacement of the motion, all you have to do is find the area of that shape. So if you have a triangular shape, use equations to find the area of a triangle to solve that. And if you have a trapezium shape, like in this case, you can also use the equations for area of a trapezium to find the displacement of said motion. Now, when you have a velocity time graph that looks like this is another thing we can learn from the velocity time graph. Velocity in meter per second and time in seconds. Now, when you have a shape like this, okay, what this means is as follows. You see this part here where it starts from rest and moves to a certain velocity here. This line here represents uniform acceleration. Or let me just show it as letters here. This part A, this being B, and this being C. Now, A represents uniform acceleration. Uniform acceleration. Now the line B, right? Line B represents constant velocity. Please note, line B is talking about this point to this point. Okay? This point to this point is B. This point to this point is A. And this point to this point is C. And C is known as retardation. Retardation or deceleration. Okay? That is, now to define each of these, uniform acceleration is when the velocity of an object changes at equal interval with time, no matter how small the time interval may be. And then in constant velocity, it means that velocity does not change over a certain time. And then retardation means that the velocity reduces over some time interval, no matter how small the time interval may be. So this same thing could have been done using this method where they label this part, say X, this part Y, this part Z, and this part B. And then you now say XY. XY is our A, which is uniform acceleration. And then YZ is B, which is constant velocity. And then ZB is C, which is your retardation. Now, these are the things that you can deduce using the velocity time graph. So what we're going to do now is we'll look at some questions on velocity time graph. We plot some of those graphs and then we solve questions using given graphs. All these things we mentioned, such as acceleration, retardation, and even the displacement of motion, we can get them using the graph. So we'll just show you how all of these can be done. Let's consider this question that involves velocity time graph. Now this says a car starting from rest accelerates uniformly till it attains a speed of 80 meters per second in 40 seconds. Now it maintains this speed for another 40 seconds, then the car slows down uniformly till it stops in a further 20 seconds. Now we have to sketch the velocity time graph, then use the graph to obtain the uniform acceleration and retardation. Now let's start by sketching the graph. Okay, now what you want to do in this case is first draw your axis, the y and x axis. So make sure they intersect. Now because we are asked to sketch, we don't have to put in so much of measurements into this, but I advise if you can do so. Okay, and make sure that you're using a ruler when you're drawing your line. They have to be perfectly straight. Please pardon my free hand drawing. Okay, so when you do yours, ensure you use a ruler. Now on this axis, the vertical axis, we're going to have the velocity, right? Now the proper way to do that is to write it this way. So we'll write here velocity and then the unit meter per second. Okay, and then on this part we're going to have time in seconds. Okay, so what we need to do now is to know that this is the rest point, which is 0. Now the car accelerates uniformly. Now when I was showing you what the velocity time graph looked like, I told you that that slanting line shows uniform acceleration. So to show the uniform acceleration in this case, we're going to draw a line like this to show that the car has accelerated uniformly. Now at this point is where we get the maximum velocity that we are given, which is 80 meters per second. So this part here represents 80, which is in meters per second. And the time taken to achieve this, remember this is to this part and this part here. Now I'm using this dotted line so that I can know exactly where it is. Now when you trace this down, that's the time taken to attain this speed, and that is 40 seconds. So I'm going to put 40 here. So from 0 to 40, from 0 to 80, uniform acceleration. Now we are told to maintain this speed for another 40 seconds. So meaning we're going to maintain this 80. So you draw a straight line, that's constant velocity, for another 40 seconds. Okay, now I try to make sure that the time interval here is similar to what is here. Okay, so what we have here is another 40 seconds. In another 40 seconds, the time taken now would be 80. right? Meaning I added 40 to this initial 40 here. Now, the next thing is that the car is then slowed down until it comes to rest. Now, to come to rest means the velocity will reduce until it gets to 0. Now, the time taken for this is 20 seconds according to the question. So meaning that we're going to reduce the time space here and then let it come to rest at this point, which is 100 seconds. Now, all we need to do is just join these two like this. Okay, so this is uniform acceleration, constant velocity, and uniform deceleration, or what we know as retardation. So now we have the velocity time graph according to what the question asks us to do. You've sketched it. The next thing is to use this graph to now find the other values, uniform acceleration and retardation. Now, the A part, uniform acceleration. Now, remember that the slope of the graph is actually acceleration. So all we need to do is find the slope of this line. Okay? So the slope, acceleration, therefore becomes final velocity. When you trace that to the y-axis, you get 80 minus initial. The initial velocity here is 0. Now we divide that by time. Now time at the final here we have 40. And then here we have 0. So basically this is 80. Now remember, this is in meter per second. And then what we have here is second. So 40 seconds. Now when you compute this will give you 2 meter per second squared. So that is the acceleration, uniform acceleration is 2 meters per second. Okay? Now to get the retardation, same process, right? But the difference is you see that the line is this way, so you're going to get a negative slope. Okay? So when we do that, retardation would be, this will be our final now. The final velocity here is 0 minus initial velocity here, which is 80. All of this divided by final time, 100, minus initial time, 80. Now this would give you negative 80 over 20. And this one is in meter per second, while this is in second. So meaning retardation is, now we know this is a negative value, but what we are calculating is not supposed to be a negative number. It just tells you that that the car is retarding, that is, the car is slowing down. That's why we have a negative value here. So you can do away with that minus sign when you write your answer. So in this case, what we have is 4 meter per second square. Retardation is 4 meter per second square, while acceleration is 2 meters per second square. And that's the answer to this question. A question like this now gives us the velocity time graph and asks us to use this velocity time graph to find the acceleration and then total displacement. Now remember, to get acceleration, we just need to find the slope of this portion of the graph that is for uniform acceleration. And then to get the total displacement, we need the area under the graph. So let's begin. Now, to find the acceleration will be the slope here, which is v minus u over t. Now, the final velocity here is given as 40 meter per second minus the initial velocity, which is 0 meter per second, all divided by change in time. Now, 4 minus 0, 4 seconds minus 0 seconds. Now, this would give you 40 meter per second over 4 seconds. So, acceleration is 10 meter per second squared. Now, to get the total displacement, we need the area under this. And you can see that what we have here is a trapezium, right? And the area of a trapezium is given as 1 over 2 a plus b h. Okay? So let's apply this. Now, if you don't want to use this method, there's another way you can do that, which is you have to break this just as we have here. You solve this triangle. Let's call this shape A, shape B, shape C. And then you solve this, you solve this, you solve this. Okay? when you solve the area here, and the area here, you then add it all together and you will still get the displacement. But let's use this and then we solve the displacement in one take. So displacement S therefore becomes 1 over 2 into, now I'm not talking about this A, maybe I should have used a different symbol. Let me call this A, then B, then C. So this one means this distance here, and then this B here means this here. Okay, so 1 over 2 into A. A is the difference between these 2 points on the x-axis. So what we have here is 12 minus 4. And 12 minus 4 would give us 8. So 8 plus, now B, which is here to here. So 0 and 16. 16 minus 0 will give us 16. And then all of that multiplied by h, which is the height, here to here. And that is 40 minus 0. Altogether, that gives us 40. So displacement therefore becomes 1 over 2 multiplied by 8 plus 16 will give us 24. Okay, then all of this multiplied by 40. You can break it easily. 2 here 1, 2 here 12. 12 times 40. So S becomes, you can just say 12 times 4, that is 48, and then add the 0. That will give you 480 meters. That's the total displacement for this question. So you see, you can use the graph to also find it directly. In this question, we are told that a train starts from rest from a station and travels with a uniform acceleration of 0.5 meter per second square for 30 seconds. Now, it travels with uniform velocity for another 40 seconds, and then the brakes are applied so that the uniform retardation is obtained and the train comes to rest after 10 seconds. So we have to sketch the velocity time graph of this motion, and then using the graph, we have to calculate the total distance traveled by the train. So let's start by getting the velocity time graph. Now for this, we sketch the velocity time graph where this is velocity in meter per second and this is time in seconds. So what we see here is that there is uniform acceleration, constant velocity, and then retardation. So easily we can just do that like this. Now another thing we have to ensure is that the timing, we can detect that using this. So the time for uniform acceleration was 30 seconds. And then constant velocity was maintained for 40. So add 40 to this and then you have 70 here. And then 10 seconds to come to rest, so making this 80. Right? Now we do not know what the final velocity is, so we call this V, while this is 0, the U. But we are told that acceleration is 0.5 meter per second squared. So we can then use this to solve the problem. Now, before you can find the total distance here, you need this velocity V. So what we're going to do is we're going to find V by applying V equals U plus AT. So basically what we have here is U being 0 plus acceleration is 0.5 and the time here is 30. So that is V here is 15 meters per second. So now we can find total distance. Now to find total distance, remember you can either break it down where this is x, y, z and find the area of this, or you just use the equation for trapezium to solve the entire area of this shape. So let's do that. Displacement therefore becomes 1 over 2. Now what we have here is 70 minus 30, that will give us 40, plus the whole of this is 80, and then multiply by the height, which is 15. Now this would give us 1 over 2. Now when we multiply this, when we add this rather, we get 120 and then multiply by 15. So easily 2 here 1, 2 here 60. So we have 60 times 15, and then our displacement is, let's multiply. So 60 multiplied by 15, this is 0, this is 30, 1 times 0, that's 0. 1 times 6, we have 6. 0, 0, 9. So we have 900 meters as the total distance traveled by this train. Now, you can try your hands on as many questions as you can find to solve velocity time graph. And if you come across any challenging question that you would like help with, please drop it in the comment section and we'll definitely attend to all of your questions. Let's look at more problems on rectilinear motion. This particular question is taken from the WAEC of 2021. And it gives us this diagram here, which is a velocity time graph. And we're told that the diagram represents the velocity time graph of a body, and we are to calculate the total distance covered by the body during the motion. Now, what we see here is that there's constant velocity at this point, and then there's an acceleration at this point. But we can do something, break this like this, such that we have this triangle, and then the whole of this forms a rectangle, right? And the area under this shape is actually the distance covered. So let's solve. Solution. So I'm looking at the whole of this as shape A and this as shape B. So the area of A, what we have there is length times breadth, and what we have here is 4. So taking this as 0, that means we have 4 multiplied by the entire length here, which is from 0 to 12, so that will give you 12. This gives us 48 meters. Now for the B part, now what we have there is a triangle, so half base. The base is from here to here, and what we have is 4 to 12, that will give you 8, multiplied by height, which is just from here to here, and we see there's 10 and 4 here, that gives you 6. Now when you work with this, 2 here 1, 2 here 4, 4 times 6, that is going to give us 24. Now all we have to do is add it up. So the displacement therefore becomes 48 meters plus 24 meters. Now let's add. This would give us 72 meters. That is, the total distance covered during this motion is 72 meters. Here's another question taken from the 2022 WAEC exams. Now the question says, the engine of a car provides a forward force of 1,240 newtons and the total resistive force on the car is 800 newtons. Now, if the mass of the car is 1,220 kilograms, determine the distance the car has to travel from rest before acquiring a speed of 4 meters per second. Now, solution. Here, the first thing we need to understand is that the effective force on the car is a difference between these two forces, the force from the engine and the resistive force. So, effective force, equals 1,240 newtons minus 800 newtons. And what this gives us is 440 newtons. Now, we should also know that F equals ma, right? So, which implies that the acceleration of the car is the force divided by mass. And the force is 440 newtons. Now, divided by the mass of the car is given as 1,220. Okay? When we break this, this would give us, now this is going to give us 0.36 meter per second squared. So now we have acceleration. So when we have acceleration and we are asked to find the, now from here you see we have acceleration is 0.36 meter per second squared. Okay, we are given velocity v. Velocity v is given according to the question 4 meters per second, and it says from rest, so u is 0, right? And we are looking for displacement s. So from here we can apply v squared equals u squared plus 2as, right? So let's put everything into this equation and find the value of s. So we have 4 squared equals 0 squared plus 2 multiplied by 0.36 then multiplied by s. So here we can then say that 16 equals, when you multiply this you get 0.72s, which means S equals 16 divided by 0.72, and this would give you 22.2, and it is measured in meters. And that's the solution to this question. This question says, what is the acceleration between 2 points on a velocity time graph which has coordinates? And then we have this coordinates 10 seconds, 15 meters per second, and then 20 seconds, 35 meters per second. Now, please, you can pause the video at this point and try it out yourself first. You already know what acceleration is and how it can be gotten from a velocity time graph. So now you have the coordinates, apply them to get the answer. Now, you then compare what you get with what is gotten at the end of this video, and let us know if your answer is correct by putting it in the comment section, whether you are correct or if you didn't get it right on your first trial. Now let's see what the answer actually is. Okay, so since we have this coordinates and we know that acceleration is the slope, right? So our acceleration will then be y2 minus y1 over x2 minus x1, where this is x1, y1, x2, y2. So definitely what you should be having should be 35 meters per second minus 15 meters per second divided by 20 seconds minus 10 seconds. So now acceleration equals, the difference here is 20 meters per second, and the difference here is 10 seconds, 10 seconds. Now when you work with this will give you 2 meters per second squared. So I hope this is what you got. The answer to this question is 2 meters per second. Here's another question. This is taken from the UTME of 1990. It says a car moving with a speed of 90 kilometers per hour was brought uniformly to rest by the applications of the brakes in 10 seconds. Now, how far did the car travel after the brakes were applied? Now, you can take a pause on the video and try to solve this yourself first. Now, I'll give you a hint. Ensure that this is brought to SI unit. Since time is in seconds, bring this to meter per second while you solve. Now, you then compare what you get with what is gotten at the end of this video. And don't forget to leave us a comment about how well you did on solving this question. So, let's solve it now. Solution. Now, first converting the velocity, which is 90 kilometers per hour, would be 90 kilometers is 90,000 meters. Now divided by 1 hour, which is 3,600 seconds. That is, velocity is going to be, now divide this and then you should get 25 meters per second. Okay, so now that we have the velocity, let's get the retardation. Now retardation. Now the reason why we are solving retardation is because the car was brought to rest. So that is, initial velocity is the 25. Final velocity is 0. So 0 minus 25 meter per second, all divided by 10 seconds. And this will give you negative 2.5 meter per second squared. Okay? And that's the retardation of this car. Now we can now apply v squared equals u squared plus 2as in order to find the distance. Okay? Now final velocity is 0, so 0 squared equals initial velocity. Initial velocity is 25 squared plus 2 multiplied by, now we have this as negative 2.5 here, and then multiplied by s. So let's see what this gives us. 0 equals 25 squared. That's 25 multiplied by 25. This would give us 5. Take the 2. 10. That's And then 2 times this, that's 10, 0 carry 1, 2 times 2, 4 plus 1, that's 5. Now 5 to 6. So we have 6 to 5 here. This will give you minus 2 times 2.5, that's 5, and then s. So we can now say 5s equals 625. So dividing both sides by 5, s equals 5 here, that's 1, here that's 2, and then 5, 125 meters. So the distance traveled by the car after the brakes was applied was 125 meters. And that's the solution to this question. Now, please don't forget that we're trying to reach as many students who need content like this. So please ensure that you like and share the video so that everyone who needs videos like this will be able to get it. The next person who needs this might be on your list, so please help us by sharing the video. You can also leave us a comment. If there's anything you would like us to solve, any particular question you have in mind, please drop it in the comment section and we'll definitely attend to all of your comments. And if you are yet to be subscribed to the channel, kindly take a moment of your time, hit the subscribe button and hit the notification bell icon as well, so that the next time we post a video, you also will be notified of it. Thank you so much for following so far. We'll be moving on from here to the next topic. I'll be seeing you in the next video. Bye for now.